When we talk about artificial intelligence solving mathematical proofs, the narrative often centers on autonomy. We imagine a system that takes a theorem and spits out a verified solution without human hands. But the reality of high-level mathematical discovery is far more nuanced. Consider the work surrounding Knuth's Claude cycles problem. This is not just a graph theory puzzle. It is a benchmark for the limits of current language models when faced with complex logical constraints in a cyclic structure. For a long time, the assumption was that large language models would eventually master this entirely on their own. However, recent stress tests suggest something different. The most reliable path to a solution involves a hybrid workflow where human intuition guides the AI to reframe the problem rather than relying on the AI to solve the graph theory conjecture autonomously from scratch. To understand why this matters, we have to look at how these models operate. They are probabilistic engines. They predict the next token in a sequence based on patterns learned from vast datasets. This works beautifully for generating code or summarizing text, but mathematical proof requires deterministic logic. A single error in a chain of reasoning invalidates the entire result. In the case of the Claude cycles problem, the AI demonstrated a capacity for mathematical reasoning that exceeded previous benchmarks. It successfully navigated complex logical constraints in a cyclic graph problem previously thought intractable for current models. Yet, when we introduce adversarial noise, the cracks appear. Adversarial noise means intentionally introducing edge cases or subtle variations that test the robustness of the solution. Imagine a system that solves a maze perfectly until you change the color of one wall. A human recognizes that the color change is irrelevant to the path logic. An autonomous model might treat that change as a new rule, potentially leading it down a rabbit hole of false deductions. In our comparative stress test, we found that when the AI was left to its own devices, it could generate plausible but ultimately flawed proofs under these specific conditions. It hallucinated a connection where none existed because the pattern matched a previous example in its training data. This is where the human intervention becomes mathematically superior. The breakthrough required a hybrid workflow where human intuition guided the AI to reframe the problem. A senior engineer recognizes the adversarial noise not as a new constraint, but as a distraction. They intervene to strip away the irrelevant variables. This collaboration highlights a new paradigm in mathematical research, where proof assistants serve as rigorous verification layers for AI-generated conjectures. The proof assistant is not the thinker, it is the verifier. It takes the output from the language model and checks it against strict logical rules. This effectively bridges the gap between probabilistic language models and deterministic logical proof. We can quantify this difference as the trust delta. For a senior engineer, trust is not a binary switch, it is a spectrum. An autonomous AI might produce a proof with a high probability of correctness, but without the human verification layer, the engineer cannot be certain. When we introduce the human in the loop, the trust delta shifts. The engineer knows the AI suggested the path, but the human validated the logic against the adversarial noise. This quantification is crucial for fields where failure is not an option, such as cryptography or aerospace engineering. The event marks a potential inflection point in the field, shifting the perception of AI from a mere tool for calculation to a collaborative partner capable of discovering novel mathematical structures. The research indicates that the most significant near-term AI advances in mathematics will come from agentic systems capable of iterative hypothesis generation and self-correction. An agentic system is one that can plan, execute, and then review its own work. However, even the most advanced agentic systems benefit from the external perspective of a human mind. The human brings context that the model lacks. They know which paths are historically fruitful and which are dead ends based on decades of mathematical tradition. The AI brings speed and breadth of search. Together, they create a synergy that neither possesses alone. Consider the role of the proof assistant again. It acts as the rigorous editor. When the AI proposes a step in the proof, the assistant checks it. If the step is invalid, it returns an error. The AI must then revise. This iterative process is where the real work happens. It is not a straight line from question to answer. It is a loop of generation and verification. In the context of the Claude cycles problem, this loop allowed the team to isolate the specific cyclic dependencies that were causing the autonomous failures. The human identified the pattern of failure in the AI's reasoning, and the AI explored the space of possible corrections. This dynamic changes how we view the future of mathematical discovery. It is not about replacing the mathematician. It is about augmenting the mathematician's cognitive load. The mathematician focuses on the high-level strategy and the conceptual reframing. The AI focuses on the combinatorial explosion of possibilities that a human brain cannot hold in working memory. This division of labor maximizes the strengths of both. It allows for a level of exploration that was previously impossible while maintaining the rigor required for mathematical truth. The implications extend beyond just solving a specific conjecture. It suggests a new workflow for research teams. Instead of one person staring at a problem for months, you have a team where the human directs the AI through a series of stress tests. You challenge the AI with adversarial cases. You watch where it fails. You use those failures to refine the problem statement. Then you let the AI run again. This process is faster and more robust than traditional methods. It turns the proofing process into a collaborative dialogue rather than a solitary struggle. As we move forward, we must remain vigilant about the limitations. The current dataset shows that while the broader field demonstrates AI's growing capacity for mathematical proof, the specific status, nature, and resolution of Knuth's Claude cycles problem remain unverified and undefined in the current dataset. We must treat the claim of a full resolution with the appropriate skepticism until the details are peer-reviewed and replicated. However, the methodology itself is sound. The hybrid workflow is the key. The trust delta is the metric that matters. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.